This is the first demo. So Mike, would you come out and give me a hand? So my little rod here is charged, and my little butterfly is charged with the same polarity, and it floats because like charges repel. There you are, Mike. See if you can keep it going. There you go. It is harder than you think. Yeah, that's a trick we learned. Now, he's got a white pipe. I have a different pipe, and I'm rubbing it with a very scientific plastic bag. No, there you go. Oh!
Okay.
All right. All right. Let me give you a hand. Let's see if we can get that going. Okay. It's a bit tricky. Yeah. Now, good job, Mike. Now, his is repelling, but look at mine. Mine is attracting a little higher. You see that? My pipe is oppositely charged. Oppositely charged attracts. The same charge repels. All right, fantastic. Thank you, Mike. So, thank you. So what was I doing there? I was busy. We were rubbing this pipe, and what we were doing is we were charging it up using a method known as triboelectric effects. Tribo being related to friction. And I've got a beautiful demonstration ball. This is my molecule. And when I rub it really, really hard, the electron comes off, and I've got a positive ion, and I've got a negative electron. And that is what creates the charge. It's from the friction of just removing these two that are here. And I will put my molecule back. And so what's interesting is that we can create positive and negative charge using this method of friction. Now, throughout the talk today, I'm going to use this little wand. It has two little colors, blue and red. What they do is they signify that there is charge, and that charge of whether it's a red polarity or it's a blue polarity, all we care about is like charge repels, opposite charges attract. So I have here two polystyrene plates, and I'm going to rub the left one with my fur. And I'm going to rub the right one with Teflon. And let me see if I can get my stick in here. Oh, I may have to rub again. So today was the worst day of all days in London to do static electricity examples. That's blue. Do you see the red? That's not a good enough red. Let's see if we can do better. Nope, we're not getting the red. The blue's coming back on. So let's try this one more time. We did see a little bit of a red earlier. I'm just going to switch wands to see if this one's a little bit more sensitive. Oh, you see a little bit of red? You saw red. Come on! All right. Yay, okay. Thank you very much. So the question is, which one's positive and which one's negative? And this is a question that we think is scientific, but in fact it's not. Most people think about polarity and charge related to the electron. Well, the electron wasn't discovered until the very late 1800s. So in Benjamin Franklin's time, when he was inventing the name of positive and negative charge, he had no idea about the electron. So he just had to guess, and his guess was glass. When you rub glass with silk, in this case I'm going to do Teflon, whatever it comes out is positive. And that is how positive is defined. Now let's see, will it do for me? Well, either one. There we go. Do you see the red? I'll try it one more time. Perfect. So red is positive. That is how positive is defined, by a glass rod and silk. In this case, I use some Teflon. So you noticed here that I could create positive or negative on the same material by using two different materials. And in fact, what they did is they took all kinds of materials, they rubbed them together, and they went to see which one was positive with respect to the other one. And they just put together what's called a triboelectric series. You can look it up on Wikipedia. And it goes through which materials you rub with which materials to get positive or negative. Now, what's interesting is the word electricity. Electricity comes from the Greek word for amber. Amber, the sap from the tree that hardens. They would take amber and they would rub it, and that would create a static charge. And that is where electricity got its name. And that's also where electron got its name, is for the Greek word for amber. In fact, Michael Faraday in this very theater would take sealing wax and rub it against something to create a static charge. And this is the first way that we, as humans, began to generate electricity. Today's talk is very simple. We're going to start with low voltage, a few thousand volts, and we hope to end today's show with over 1 million volts. If you're wondering, how can I demonstrate 1 million volts? It will make a spark 1 meter long. I hope that demo works. All right, so now I want to show you a couple interesting things we can do with electricity. I've shown you the triboelectric. The next thing I want to show you is induction. So, gets too much there. So what is happening is my charge here is inducing a polarity on the can where the opposite charge is on one side and the like charge is on the other. And to share that with you, I actually have this balloon here. And it, in fact, will operate just like the can. So what we have is this is charge negative, which means all of the negative charge runs to the other side. And that leaves this side positive. Opposite charges attract. The positive is then attracted to my negative stick, as we can see right there. So what I do is I induce a difference in charge. And this difference in charge is going to be one of the ways that we start to generate higher and higher voltages. Now, I have just shown you that demo. I saw that demo myself when I was younger. And I asked myself, how do I know he's just not making it up? I mean, really, did any of you see the electrons run over to the other side? Or the can? No. So I said to myself, how do I prove that this is really what is going on? And so I would like to demonstrate that for you. So I have here a Van de Graaff generator. You may have seen it before. I will explain how it works later. For right now, I just want it to generate a bunch of charge for me. And sorry about that. So my little charge wand here, I'm just going to turn it on. Turn on my wand. It is red. Everybody see it's red? Okay. So what I'm going to do is I'm going to take two pieces of metal, and what we're going to do is, let me just do it the opposite. Oh, there we go. Here we go. So if red is negative, all the negative charge will want to go over here, and this will become positive over here. Key thing is, you notice they're touching, right? They're just like the can, one continuous piece of metal. So what I'm going to do is I'm going to take both of these off. I'm going to touch them together. And now, I told you before a field was induced. You shouldn't believe me. How can I prove it to you? I separate the two. And if this really had, no, let's go back in. Ah, there we go. This was red. Let's reset the red. These things go a little crazy when this is on. Let's bring the red. Let's reset. There we go. We get a blue on both of these now, on both of those. So I'm going to reset. It just does not like, you know what I'm going to do? Put them close. going to separate. Let's see if that makes this behave better. That was red. That was blue. All right, blue, red. Will it come back on? No, it won't come back on. It's already lost. So there I've separated the charge into two pieces. And this is how we're going to generate higher voltages, because we can induce charge and then we can separate things. Now, I want to show you the next way that we generate high voltages, and it's called electrophorus. And it is using the induction that we just spoke of. So what I'm going to do is take my fur, I'm going to rub this, and now let's see what we get. Blue, nothing. I'm going to put this on top. I just put nothing on blue. Do I have any more charge than the original blue? No. So I should be able to go in and see my blue, unless it's leaked off already. There we go. I was just touching that. Can we get a blue? Can we get a blue from anybody here? There we go, we got a blue. There's our blue. Now, what I'm going to do is I'm going to come in with this stick, and all I've done is I've taped a neon bulb to the end of the stick. And when I get a spark, you can't see it, so I'll just say ouch. But I wanted to show you one spark, so you know we did get sparks. Can we take all the lights down? All the lights down. Did you see it? Okay. So what I've done now is I've taken all of the charge off of here. So there's no charge. I'm lying to you here as I bring things around. So there's no charge on this. And here's the question. Is there really no charge? Or do I now have an equal and opposite charge on the metal plate as I did on the polystyrene plate? If I take them apart, let's see if I can measure blue, red. Blue, red. Right? So what I have done is I've actually created blue charge by letting all of the red charge that wants to repel go into my hand, and then what is all left is the blue charge here. And so in doing that, I'm able to create charge on a separate device. Now, that was a little bit of a spark there. Let's just pick this back up. I can touch. I could transfer. I could touch. You can't hear it, but a spark. 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 You getting the idea? So I could actually do this all day. And if I had a good insulator and the charge wouldn't disappear, I could do this for the rest of my life. Okay? Now, people sometimes say, well, isn't that free energy, free electricity? No. Have you not seen me touch it, move it, touch it, move it? I'm doing the work. I am pumping the charge in and out, and I'm doing the actual work. And that's how we get the work, but we can transfer that out of here. So now, what's interesting is, I want to show you with this little device, and I'm going to pull this up. We have a roaming demonstration camera here, and I think Mike's going to try to zoom in on this. So what I want to do is I want to charge this up. Could we get the theater, oh, this is good. You guys can see me. And now I'm going to change this. First of all, let's reset this to 0. Okay, we agreed 0. Oh, I did it backwards. It's got to go down, touch, transfer. And notice it stays at about 1.7, right? Don't look at the one that changes. That's just because I'm moving the plate back and forth. 1.4, 1.7. You may say, well, maybe you lost all your charge here, so I'm going to put a lot more on. Transfer it over. Oh, we got up to 2. That was pretty good. But I really can't get above 1.7 or 2. Now, why is that? It's because I can only transfer charge, let's go to black, when the potential of this is higher than the potential of this. The potential for electricity is voltage. So when this has a higher voltage, I can transfer charge. When they're at the same potential, I can't. And so what I have here, just to kind of illustrate this, and Dan, could you take the plinth away? Thank you. So I have two beakers of water here, and I've already pre-siphoned them. And what I'm going to do is I'm going to pour water into here, and the water is charge. And the charge is being transferred from one to the other through this tube. Now, intuitively, will this level ever get higher than that level? No. It's exactly the same here. This potential can't get any higher than that potential because we can't transfer any more charge when they have the same potential energy. So we need to figure out a way to get to higher voltages. And what I'd like to do is I'd like to introduce you to a pretty amazing apparatus here. This is Lord Kelvin's water dropper. Lord Kelvin demonstrated this here in the theater. And I'm going to get it working, hopefully. And what we're going to do is turn down the lights so you can see it operate, and then I'll explain it. And so let's go ahead and get it started. Sometimes takes a little bit of all right. Okay, it's started up now. So if we could turn down the lights and just look to where my hand is for a little flash. Could we get the lights up just a little bit so I can check the meter? There we go. Did you see it? Back down. Now that it's flashing, let's see if we can get another flash. Will we get another one? I think we will. There you go. Did you all see that? So what we're doing is I'll let this run for a little bit. Do you want to hook up the electroscope? What we are doing is we are creating charge from nothing. So first off, there's no current in these. I decided to make this out of copper pipe because I thought it looked nice. But what's happening here is that we are actually inducing charge, and I want to just go over to our little explainer here. Remember I told you about charge separation here, right? So let's go over here. As the water comes down, these two circles are charged. As they come down, we polarize the water, and then you notice what happens. The drop falls, right? The drop falls. So the drop, who had an induced charge, falls away, and as a result, the water drops have charge. What we do is we create positive charge in this one. The positive charge repels the negative. The positive charge comes over here, attracts the negative. This goes down, this becomes negative. The negative comes over here, it attracts positive, and it's a feedback loop that goes back and forth on itself. Now, Michael, is that working for us? Yes. All right, excellent. Can we get the camera up on the screen? It's working very well now. So if you look, as the voltage increases, they spread apart, and then there you go, that's perfect. That's great. That's great lighting. Spread apart, and then we get a spark that comes out there. We're building up the charge until we get a spark across here that lights up the lights. Now, I want to show you that indeed this is how it works. So first off, I have here a charge stick. This is just like the fur and the PVC. It just does it automatically for me. So if you don't believe that water can be polarized, do you see that? Right? I'll do it for this side. See how it's attracted? It's attracted for the same reason the balloon in the can was. And so what I can do, I'm going to turn this back on, and I'm going to zero that all out. All right, do you want to come and see if you can get the screen? So what I'm going to try to do here is the water's going to flow through here, and I'm just going to charge this up, and just look at the number. There you go. You see it going up? All I've done, I just have one loop here that I charge. It creates polarized water, which creates charge that flows down into here. And that is how the Kelvin Thunder water dropper works. All right? Thank you very much, Michael. Now, this was an interesting machine because it uses induction and It uses gravity to do the work. The gravity is the one that's going back and dropping all the water drops and separating everything. There's other machines out there. How many of you have heard of a Wimshurst machine? Anyone? A few of you? Well, we have from the 1933, I believe, Christmas lectures, the original Wimshurst machine that was used there. And I'm going to explain this in a minute, but I wanted just to first for you to see what it does. Go ahead and start it up, Dan. Everyone see? I think probably you can see with the camera pretty well there. Everyone see? All right. So the question is, how does this generate charge? Most people think, well, there's something spinning inside. It must be friction. It is not. It is induction. All right, Dan, let's turn it off. And of course, being at the Royal Institution, we can't have a small Wimshurst. We must bring on a giant Wimshurst in order to explain this. So if we can get the demo camera to come in tight to the disc here. So if you'll notice in the Wimshurst, we have a disc with metal foils on it. Let's see if you can maybe, you guys see them right there? There they are. And we have the discs running. Here is my giant Wimshurst. Now, I'm going to share with you the secret in how this is able to create much higher charge than we could before. Remember our 2 beakers of water? We couldn't go any higher than our source. What the Wimshurst is able to do is to actually generate higher voltages using induction, and here's the key. So, if I were to place my metal pan above this, charge the bottom, and touch the top, you could say, oh, well, you're going to induce a charge. We already saw you do that. But remember that with my little wand, when the two are together, I had equal red and blue charge. Because the blue is made from the red, I can never have more. So I never get more charge through induction when I just have one pan or the other. Take note, however, of, in the Wimshurst, there are 2 pieces of metal next to the one that my special electrode is over. And I put it to you that these 2 will induce a charge on this. And I want to demonstrate that to you. What I'm going to do is I am going to charge up those 2. See if our wands will cooperate with us. I'm going to charge up these 2, but not the center one. So if I get any charge on this, it must be from these 2. And I'm going to take my charge stick. Charged up these 2. Let's see if this will... They're both red, I think. Yes, okay. By the way, the reason you sometimes see the blue flash is when I move it, it gets an induced current in it, so that's why it's there. Very slight spark. You see? My charge is now blue. So what I've done is I've charged up these 2, and I've induced a little bit of charge on this. So now what I'm going to do is charge up the middle one, charge up these 2. Those really were charged up. Just got a spark. I'm going to get my one charge from the bottom, plus a bit and another bit. So 1 plus 2 bits. Then I'm going to rotate my wheel, and I'm going to do that again here. I'm going to do that again here. I'm going to do that again here, here. Now, while I'm doing this on the top, there's a partner of me on the other side charging up these bottom ones. When we come back around full circle, each one of these has 1 plus 2 bits because they are equivalent to the one I did before. So now I have 1 plus 2 bits, 1 plus 2 bits, 1 plus 2 bits. So I'm immediately going to get 1 plus 2 bits on here, plus a contribution, plus a contribution. I have more charge than I did originally. And then I'm just going to circle back around. And now I'm going to have even more charge. And I will build up charge just like the Kelvin water drop. Did you notice I didn't start it? It started by itself, just a little bit of charge imbalance, and then it has feedback that builds more and more charge. And so the secret of the Wimshurst is the fact that I get the charge from the one right beneath it, plus the two next to it. And that's how I get more charge every time I spin around, because as I spin, they come back, and I can add the more charges from the sides. So that is the Wimshurst. If we could take that off, and I'd like to show you some classic demonstrations from the Royal Institution with this beautiful example of a Wimshurst machine. And Michael, if you can clear the buckets. Clear the buckets when you have a chance. Thank you. Great. So we're going to start with the first one. And I don't know if many of you are hunters, but we have here a hunter. And this hunter is going to be hunting some birds. And what we're going to do is we're going to charge this up, and the birds are going to get charged, and because they're the same charge, they're going to fly apart. So let's go ahead and turn it on. Let's see if we can get the birds to fly away. All right, so now the hunter is looking for the birds. Can anyone help the hunter? Anyone help the hunter? Where should I go? Maybe in this direction? Excellent, excellent. He's looking around for some more birds. Fantastic. Comes back around, and I'm just going to, for this side over here to see, oh, he keeps on shooting the birds. So you guys can see there. And now he's just really going after all the birds that are there. All right, Dan, thank you very much. So that is a classic demonstration of sparks in a fun way. We are now going to do one more demonstration that is the Thunder House. And Dan's going to pull it out. And how many of you have heard of a lightning rod? Okay, everyone? How many of you believe that Benjamin Franklin actually took a key and put it up on a kite and flew it? No, I don't think that's actually what happened. But he was one of the first to realize the power of being able to guide electricity and charge, realizing that the lightning we see are the same as the sparks we see down here. So what I have here is a lovely house. We use the other. Nope, Dan is right here. Here's what we need. I think you're missing a bit in the center, though. Ooh. Excellent. So I know this piece, my understanding is dates back to at least the 1930s, and I believe our head of heritage said perhaps a little bit earlier, or maybe even a lot earlier. I think it goes just in with friction. You squeeze it like that. Okay. So we're going to start with, can we get the demo camera to come around? You can already tell this is going to be fun. I have to put on safety, my PPE, okay. So what I'm going to do is I'm going to put on a lightning rod. Can you come around and take a video of the lightning rod, the camera up there? So here's my lightning rod, and it's going to go right down to the ground. And I'm going to just ground that. There we go. All right, so now any lightning that comes in should go straight down the lightning rod, and we should all be safe. Dan, would you start the Wimshurst? Okay, we're building up. Okay, we've got a little bit of lightning there, you see? Right, it's not damaging. No one in the house is dying. No one is catching fire. Everyone's very happy. So the lightning rod is a really, really good thing. All right, so what we're going to do now is I'm just simply... By the way, in preparing for these demos, that happens a whole lot. There we go. I'm going to just adjust that. Now what I'm going to do is I'm going to take away my lightning rod, and now my poor house is unprotected. Unprotected. Now, I just want to refer you to what is on my eyeballs, and let us see what happens in an unprotected house. Go ahead, Dan. The house is apparently just fine. Well, I'm not sure we can open up this house to see what happens inside. Okay, he's going to try a bigger spark. So I hope everyone will now have a lightning rod at their home. Thank you, Dan, also for that sage advice that we should get a little bit larger spark. So that was the Wimshurst, and what I want to do is I want to come back to the Van der Graaf generator. Van der Graaf was a professor at MIT, and he invented this generator in the late 1920s, and it's become very popular, and many people see it in large areas. Let's just go ahead and start it. Everybody can see the sparks. Everybody sees the sparks there? By the way, our cameras hate the sparks. So if you see a blue screen, that's what's happening. Okay, so this is the Van der Graaf. It's generating around 100,000 volts. Up until now, we were around 10,000. The Van der Graaf's getting us up to 100,000 volts, and I'm just going to turn it off. And I want to show you how it works. So I'm going to take the top off and place it right over here. Okay, I'm just going to turn it on so that everybody sees that there's a belt going up and down. Everybody see that there's a belt going up and down? And so there's little people inside that are adding charge to that belt, okay? There's two ways to add charge. One is with friction. You can actually make the rollers a different material, or you can actually use a high voltage source to do that. But when everyone explains the Van der Graaf, what they do is they just explain the charge moving up the belt from here to here. What they don't explain is the key innovation of what makes the Van der Graaf really special. And I want to show that key aspect phenomena right here. This is what Professor Van der Graaf figured out. So I'm going to place on this a few thousand volts. And let me turn this on. Okay, so now I have a few thousand volts on this. And what you want to pay attention to is this number. Just want to make sure. There we go. So I've got a few thousand volts here. Hopefully when I touch it, we can see the number go up. Don't touch it, David. It's a few thousand volts. Okay, so this is just like the belt, right? I'm transferring the charge. If you think this is getting old, try practicing this. Okay, we're up to 46, 47, 48. We're not really getting much above. That makes sense, right? Because of this, okay? So it doesn't seem like we could get to 100,000 volts if we're just putting charge here and floating it up, because it just could go as much high in potential as our little men down here could do. However, let's do something slightly different. So what are we at now? Can you go back to this number just to see where we are? Okay, I'm just going to get it back up to... All right, now, is that 48? 41, 40, okay, watch now. It's only a few thousand volts. All right, we're gonna have to charge that back up. So let me zero that out. I apologize. Okay. I got to go back and do it. I'm sorry. Is the number not changing? There we go. It's kind of therapeutic. Okay, there we're stopping at around 41. This is not going where I want it to go. I think the humidity's gotten to me. We're at 50. We were never at 50 before, were we? Of course, I touched the side. And then we go back down. So you saw that we went above. And what it is that the Van der Graaf is actually a Faraday cage. The potential inside of here is 0. So in the outside, we charge it up and we can't transfer any charge because it's at the same potential. But the inside, all the charge cancels, and we can continually flow charge in there. Mike, could you come out with a bucket? You have the bucket right there. So that is equivalent, if you remember, we had our little demonstration here. Let's turn that down. All right. Mike has the bucket there. I'm going to lean this over. And now imagine the potential in this one was 0, as it is inside of a Faraday cage. I could keep adding charge over and over and over and over again. Am I spilling? Yep. Thanks. And this is how the Van der Graaf works, is by putting the charge in the center, we are able to put much more charge. In fact, we could put an infinite amount of charge into this. When we put it inside, the charge goes to the outside and it's 0 inside. We can charge this up until this starts to break down the air. And the shape that breaks down the air the least is a sphere. And so that is why a Van der Graaf has a sphere. But the key piece is the Faraday cage. And you notice the little man who put the charge on that goes to the top, the charge goes inside of the dome. And that is what's key to how a Van der Graaf works. So we've done up here, all of these have been DC charge. I want to start taking you into some other areas that we can look at. So over here, I have what is called a Ruhmkorff coil. So I should start back. We're at the Royal Institution. Michael Faraday discovered induction. This is a replica ring. So what he discovered is if you put a current through one side, can we go, oh, wait, let's get it up there. A change in current in one side will cause a change in current in the other. And in this one, he has an equal number of turns on these. And this is the basic idea for what is known as a Ruhmkorff machine. And that is not the inventor, but rather simply the instrument maker that made the best instruments. This coil is the same as the original spark gap transmitter. And what I did is I bought one of these, and if we can go black on the top. And I bought a second one and I took it apart to see how it worked. And so what we have inside is we have one coil with maybe 200 turns. And then we have another coil with maybe 2,000 turns. And the way this works is we have a change in current in this coil, and it gets multiplied by the difference in coil numbers. So we have sort of a lever to get us higher and higher voltages from this second coil. That's the first thing that this does. The second thing is the voltage this produces is related to how fast we change the current. So the faster we can change the current in this, the higher voltage we will get on that. And so our core is to do lots of currents, high turns, switch it fast, and that is exactly what is inside of this machine. And I'm just going to turn it on so that you can. So that's what happens. We're able to create very high voltages by using electromagnetic induction. Now, this machine is a lot smaller than the Van de Graaff, and it becomes a much more popular machine for us to generate high voltage with. And many of you may say, well, this is all fine, but I live in a normal household and we don't have Tesla coils and Wimshursts and these others. However, it turns out that any of you who owns a petrol car indeed has a Ruhmkorff coil in it. So I have here an induction coil, and you may not recognize this because you haven't looked at your engine recently, but you might recognize this as a spark plug, right, for a petrol. So this is what charges up the spark plug. And what I do is I have a little oscillator here that's going to turn on and off the current, on and off the current, and that oscillating current should generate for us a spark. Let's turn the lights back up. And so in every petrol car, you have your Ruhmkorff coil in very much the same way. There's two coils in here with a core that helps couple them together. Now, we've done this, and we've generated these high voltages, and now what I want to do is I want to show you some applications of high voltage. So I have over here, this is the one that was shocking me earlier. This is just a smaller version of that one, and it generates around 30 to 40,000 volts. And Dan, do you have an instant? Yeah, thanks. So what I'm going to do is I'm going to turn it on, and what I have here, can we get the demo camera to come in close? Very close. So what I have is a sharp point, and then these cylinders are not nearly as sharp. And what's going to happen is near the sharp point, I have a really high electric field, and it is going to rip the electrons off the air molecules. And now the big heavy ion, the ion is the molecule without the electron, it is going to be accelerated through the electric field from the tip to the cylinders. Now, this is big and heavy. If I'm creating the electric field, the force that moves this has an equal reaction to me. So it pushes on me in the opposite direction. So we're going to push air this way. It's going to push back a little bit on this, but let's just see how much air flow we can generate from these ions flowing from the sharp to the rounded. Okay. It's a lot of air. There we go. We get that? You see that? That is all caused by the electric field making ions and then accelerating them towards the less sharp coils. So this is known as an ion thruster. And if we can have an ion thruster, do you think we can meet an ion spacecraft or an ion craft? Yes? So let's see if we can make one of those. I have here an ion lifter. If you could zoom out, we could take a look at our nice triangle here. And what I'm going to do is the same, and if you, I guess close in a little bit. If you can see, there's a sharp wire at the top. And that sharp wire is the same as the nail. And then the bottom side is smoother, and so those ions get accelerated. Remember, they get torn apart at the sharp place, and they always accelerate to the smooth place. They don't get torn apart at that smooth place. So I'm going to turn this up, and hopefully we can see if we can get something to fly. Dan, if you want to take the incense. You see the air going through? Going directly down there. So we're able to use that electric field to accelerate ions to allow us to achieve actual flight. It's pretty cool. Excellent. So this is some of the things we can do with these Ruhmkorff machines. And here I created some ions. I want to talk now about something called plasma. Plasma is simply a collection of charged particles. They could be ions or they could be electrons. And we can do all kinds of interesting things with plasmas. And I want to show you a couple of these in these next 3 demonstrations. So first off, what should you never put in the microwave? Grapes. Yes, that's correct. So I have here a grape. Just going to cut it in half. So I've just cut a grape in half. Now, if you can take a look with the camera, let's just set it up. All right, so what is happening? Why did the grape catch fire? It's like a tuning fork. So the microwave runs at 2.4 gigahertz, which is very fast frequency, but it turns out the wavelength inside of a grape is resonant. If the grapes were too big, the grapes would be too big to have resonance like a tuning fork. So what we're trying to do is tune our fruit to the exact resonance of our microwave. So that's a pretty cool demo, but you probably, for those on the side, you may have seen a little bit in here. It's kind of annoying to look through here. So Dan, do you have any ideas on how we might be able to look better into the microwave? What are you going to do, Dan?
Hole in the back.
Hole in the back. Only at the Royal Institution would we drill a hole in the back of your microwave. Please don't do this at home. We are not responsible. And there you go. It's a little bit difficult to drill a hole there. Dan, I'm going to give you my phone, and I think you know what to do. So what we're going to do is I'm going to light. The other thing you should never do is put fire in the microwave. So I'm going to light a candle, and you're going to want to see if we can get a picture on the phone of what's there to put that up there. So I'm going to light my candle. Now, why am I lighting a candle? Because a flame actually ionizes the air. So we're going to get some ions from this candle, and my hope is that maybe the microwave can achieve a resonance that causes a plasma to form. And if you're like, what's a plasma look like? If we're successful, you'll know. Going to get it again. Going to let that have a little bit of air. But there we saw a plasma generated inside of the microwave. I will give it one more shot to see if we can get a little bit longer lasting plasma. By the way, part of the problem is the tea light wax doesn't like the microwave. I haven't figured out yet why. All right, there we go. All right, well, we saw it the one time. We could be at this for a while for the microwave, but that's one fun way to generate some plasma. Thanks, Dan. Now, there are some other interesting ways with the Ruhmkorff machine that we can generate some plasma. So Up until now, when we talked about the ion lifters, we were talking about electric fields in air ripping apart molecules. What happens if we remove all of the air? If we remove all of the air, then there's no ions. The electrons are now free to flow from the two connections. And that's exactly how a vacuum tube works, cathode ray tube works. And so what we're going to do with the Ruhmkorff machine here is I'm going to turn it on, and we are going to take the vacuum out of this. And initially, we're going to see a spark right here. And that spark is going to die away when a plasma stream of electrons starts to form over here. So let's keep it black until this forms, because I think it disturbs the camera. Go ahead. Thank you. You see it forming? How's that? So this is a stream of electrons going between the top ball and the bottom. And someone asked me once, well, are the electrons going from the bottom to the top or from the top to the bottom? My answer is, I don't know. When J.J. Thomson discovered the electron, this is indeed how he did it, was to look at the fact that the electron is a particle. There is no particle of positive charge, so he could actually look at the physical transfer of electrons. Now, this is super cool, but it probably does not surprise you, turn off the vacuum, that in the late 1800s, it was very popular in towns such as London, at the Royal Institution, to do as amazing a demonstration as you could. And there was one particular demonstration that was very famous for using the Ruhmkorff coil, and that was called Gassiot Fountain. Sorry, my French is horrible. And what we're going to do is we're going to take this out. And now I'm required to tell you that there's two precious items in here. They are not from the archive. However, this is just a really cool box. So I'm going to pull this out. So this is simply a glass goblet. It is green because it's impregnated with uranium. That's how they used to make green glasses. And there's just a bit of tin foil in the top. So now I'm going to place this here. We're going to do the exact same. And the ball is not really touching the tin foil inside. That's not so critical. And now we are going to try this demonstration one more time. You may want to video this. If you do, make sure your light is off, your torch. Just want to make sure our seal is good. Could I get a little bit of the house lights? I just want to check our pressure. We are going down. Okay, we're going to turn it off and give it another quick try here. Turn that off, thank you. I think our vacuum may not be down quite enough to do this. Start it again, please. There we go. It was worth, I think, the wait. The charge is going into the glass, outside, and back down. And it is a fountain all around. the glass. And you have to admit that would be very impressive in this exact theater in the late 1800s. And this is one of the really pretty things we can do with plasmas. Now, there's one more plasma that I would like to share with you. And it is a very special plasma. So I have here an apparatus that my students made. And it contains an oscillator. And an oscillator is just like a swing. And we're going to circulate a current. By the way, this is just a wire. I made it out of very thin tubing because it was nice and rigid. So we're going to oscillate a current in here. And if you remember from physics class, the current will have a magnetic field that wraps around. So we're going to have a magnetic field that circulates around here. Now that in itself might not be too exciting. So I want to add one more piece, and it is once again in our special box. So this is a bespoke globe, 2 liters, filled with xenon and nothing else. And what I'm going to do is place this right there in the center. Okay, now I'm going to touch it. There's nothing to be seen. Just take the lights down real quick. There's nothing there. Let's bring the lights up a little bit. So, add a little power. Okay. Nothing there, nothing coming on. So, what I want to do is I want to induce, if you remember induction was what we learned earlier, I want to induce some charge near the edge, and hopefully that charge will then start to circulate in the magnetic field. And maybe we can get some glow or maybe some other very interesting phenomena. And to get that out, what I'm going to do is take my stick as I did before, and let's see if hopefully there's not enough moisture. Let's take the lights down. So now what we have is we've created an imbalance of charge that's now circulating around, and I can come in and touch and create some amazing things. This is a plasma toroid, and it forms and becomes a steady state inside of the globe. When you saw those little streamers, those little white streamers, when those streamers come back on themselves, I'm going to turn it down and see if we can't get the streamers back. It's going to float back to the top. And so if I can get one of these to circle back on itself, it'll form a complete circle circuit, and then that will suck all of the charge in to form the plasma toroid we just saw. And of course, last time it happened quickly. And there we are. It is thank you. It is completely self-sustained inside, and I just lower the power, and you can see it slowly rise up in case you didn't believe it's actually floating inside of the globe. And so this is Gassiot's Fountain for today, for 2023, is right here with the plasma toroid. Thank you. Can we have the lights back up? Thank you, Michael. It was kind of you to loan that for us. And so now I want to talk about our final instrument. You've probably already seen it here. How many of you recognize this guy right here? This is a Tesla coil. And I'll have to ask Charlotte here. Do you remember what year that Tesla lectured here? By any chance? 1890, Tesla stood right here and did a demonstration of his Tesla coil. Now, what is different about a Tesla coil than this Ruhmkorff coil is, how many of you pushed someone on a swing? Yeah, everyone? Okay. You maybe even have swung yourself and kicked your legs and got you up, did you have to lift the person all the way to their maximum height? No. You just add a little bit of energy and the swing starts to resonate. What is different about a Tesla coil, these Tesla coils, is we have the same inductor that we had on our Ruhmkorff machine. However, now we have a capacitor. It doesn't look like a capacitor, but when you're 100,000 volts or 1,000,000 volts, this is a capacitor. And this is going to resonate with the coil to produce extremely high voltages. You can't see it very well. Do you want to come in close? Might help you to see. There's a little bit of you can see some windings here, perhaps. That is the initial coil, and you can see this is about 5 turns, and this is about, I don't know, 800 turns, 1,000 turns. My student has wound many, many of these. So let's get and take a look at what this sounds like. Okay, so just for safety reasons, I want to check everything. This is a point, if you have any issues with ozone, should be fine, but we will be generating a lot of ozone with this and the other final demonstrations. So most people think that maybe a Tesla coil is continuous, but it really just comes on for 20 microseconds, a few millionths of a second, and then turns off. All right, now it's just showing off. So why do we hear it? We hear it because it's ripping apart air molecules, and that's creating a vibration in the air, which our ears can hear. So it's those ions moving in the electric field that causes the noise. And one of the really fun things that we can do with Tesla coils is they actually can play music. Let's see if we can get our Tesla coil here to play us a nice song. Okay. If we can hold with the lights, I just hit the wrong button, sorry. All right, let's give the Tesla coil a round of applause. So now, this is an amazing little Tesla coil, but like the Wimshurst machine, this really isn't big enough for the Royal Institution. So I brought all the way from America my own Tesla coil, which is so dangerous that they required that I put it inside the Faraday cage from the 1933 Christmas lectures. And here we are. Now, what's great, if we could bring the house lights up, this one can also play music. Now, if both coils can play music, do you think we could ask them to do a duet? Would you be willing? Yes. All right. Now, if I recall, I did promise you 1,000,000 volts. Do you recall how big the spark needs to be? A meter. In the US, it only has to be a yard. It's lower voltage in the US there. All right, Dan, could we take the Tesla coil out? Yes, we are. And Dan, if you could place that approximately a meter away, and maybe bend the tip down a little bit. There we go. If you're all wondering, this is a fiber optic cable to keep me alive. So I think we're just going to, if you can lock this up, Mike, we will get this tested away. I think that's good. So let's just test it out a little bit, see what happens. Now I want to pause here. I want you to look at the two fluorescent lights and notice that the one on top the Faraday cage lights up and the one inside does not. Let's take the lights down again. Can you see that? Excellent. Now, if we take the lights back up, we were having a discussion with the demo team, and the question came up was, is it safe to go inside of a Faraday cage? And my answer was, in theory, yes. And they said I should show it in practice. So, for safety reasons, I need to unplug myself, lest I be a Tesla coil inside of the Faraday cage. You got it, Mike? All right, wish me luck. If I don't see you, thank you very much for coming again. We take a pin off as well. Yeah. It's going to be fun. All right, Mike, you promised 1 meter.
Yes.
Hold on a second. We can turn down the lights so I can do a prayer, please.
If he still has the power of speech. We've got a few thank yous to do before we thank Professor Ricketts again. My name is Daniel Glazer. I'm the Director of Science Engagement here. And before I give context to... Where's the Faraday box? Before I give context to what David has shown you today, I think he's got a few thank yous that he wants to give. And so I wonder if I can ask the demo team, that's Dan, Mike, Isla, Tom, Charlotte, to come out, because without these guys, come on, Charlotte, you have to move down. None of these would have been possible. Here, Ed.
So, why don't we get Dan? Dan, I have something in the box for you. Come take a look.
I'm getting in the box.
You're getting in this box. That is going to be the most amazing demo I've ever seen.
Thank you.
There you are, a little inscription for you. I think you need the microphone.
Oh, you want me to read it? Okay. To the RI demo team, the most amazing people at the most amazing place keep inspiring us all. Professor Ricketts, 24th of the 6th, 23. You even did the date the right way. Well done.
Thank you.
Thank you very much. Unbelievably kind. Thank you so much. Professor Ricketts, everybody!
So we do need a little bit of history for this. We got an email a couple of years ago, Charlotte and I, from this guy in Harvard who was a fan of Michael Faraday's. And although he was originally an electrical engineer, his day job is doing innovation. But he decided to come here and do a bunch of experiments to lead to the end of the journey, which culminated in the electric motor. And if you've been to the museum downstairs, you'll see the world's first electric motor was made by Michael Faraday. And we thought that would be a fun thing to do. And David came towards the end of the COVID time. And over the last couple of years, he's demonstrated the most extraordinary generosity to the RI, not least because he's given a bunch of sweatshirts and lab coats with his own initials, or the first two letters of his name, to the RI. But also he's developed, again, at his own instigation and with his own funding, many of the things that you've seen here, which I think is fair to say, David, you will not see anywhere else in the world. Most of these demos do not exist.
You will not, there is not the cup and the toroid you will see nowhere else.
Correct.
I don't think the cup's been shown for
It's here 100 years. So there are things that you'll see here which are practiced and easy, and there are things that are at the very edge, both of technology, safety, and practicality. And this evening you've been taken to the very edge of that, but in a way which, as David has said, since 1799 has been happening in this theatre, and a lot of the discoveries and the technology that he's shown are from this very place. The Wimshurst machine, for example, you can see when you go outside, is in the painting at the back there, which is normally in the display case. But what he's done for us, and I think for us as individuals, for us as a community, and for the people in the demo team, is to take stuff out of their cases and put them to use, which is like we like them to be at the Royal Institution. So with that historical context, and at the very cutting edge of science and safety, we've had an extraordinary evening. Please join me once again in thanking your lecturer this evening, Dr. David Ricketts.